The modern wireless systems are shifting towards higher carrier frequencies, wider bandwidths, and larger apertures to satisfy the data requirements of 5G and beyond wireless systems. This leads to breakdown of conventional models based on the far field and narrowband assumption. Hence, it is crucial to investigate the transition to near field and wideband communication and understand the fundamental limitations of the conventional signal processing solutions. Hello everyone, I am Nitish Deshpande, and today I will present my research on the topic a wideband generalization of the near field region for extremely large phased arrays. This research was recently published in IEEE Wireless Communication Letters. I will start by discussing the transition from far field to near field communication. Consider a source which radiates spherical wavefront towards a receiving aperture. In this animation, we observe that the spherical wavefront can be approximated as a plane wave. This corresponds to the far field scenario where the plane wave approximation is done to simplify the signal processing at the receive aperture. Now, when we increase the size of this receive aperture, we see that the same spherical wavefront cannot be approximated as a plane wave. Hence, although the physical distance of the receive aperture from the source is the same, the scenario is considered to be near field. This is because of the increase in the receive aperture, because of which the planar wavefront approximation breaks down. For the plane wave approximation to still hold, we need to move the source away from the receive aperture. So the near field region increases with the size of the receive aperture. I will now discuss the effect of transition from narrowband to wideband. Consider a phased array consisting of phase shifters designed at the center frequency Fc. A phase shifter modifies the signal phase without any change in the signal amplitude. For the narrowband case, there is a single beam which radiates towards the user at the design frequency Fc. For the wideband case, which is comprised of multiple frequencies, the beam splits into multiple directions at different frequencies. Hence, for a user located at this point, the remaining subcarriers experience a beamforming loss. This effect is called as the beam squint or beam split effect. This is a fundamental limitation of the phased array because the analog beamforming applies the same phase over the entire bandwidth. Hence, the beam shifts direction due to mismatch between the wideband array response and the narrowband beamforming phase shift. This effect exacerbates with the increase in the aperture. Hence, the increase in aperture leads to the wideband and the near field effect. Prior works on this topic individually analyze the near field and wideband effect. However, as we see that both of these effects are linked, so in our work, we jointly model the near field and wideband effect to characterize the limitation of a phased array. For comparison, we consider four different channel models. The first one is the far field narrowband, second one is the far field wideband, the third one is the near field narrowband, and the fourth and the most general one is the near field and wideband channel model. This channel model considers the beam squint as well as the spherical wavefront effect. The performance metric is the normalized beamforming gain in dB on the y-axis, and we plot this as a function of frequency in gigahertz. For the four different channel assumptions, three of them are approximations of the most general assumption of the near field and wideband model. In this figure, you can see that the blue plot, which is the far field and narrowband approximation, overestimates the beamforming gain in a near field and wideband scenario. We see that the joint effect of wideband and near field phenomena is more severe than the individual effects. The problem that we tackle in this work is defining the near-field transition boundary for a wideband system. We propose the bandwidth-aware near-field distance, which is the smallest distance beyond which the beamforming gain is always above a certain threshold. Here we consider a contour plot with distance on the y-axis, frequency in gigahertz on the x-axis, and the z-axis as the normalized beamforming gain. Here each contour corresponds to a particular beamforming threshold. As you can see, for a higher threshold, there is a smaller bandwidth. You see that the minima in this plot occurs only at the center frequency, and as the frequency is offset from the center, the distance increases. Hence, we conclude that the near field region increases for the wideband system. On this plot, we also mark the conventional narrowband metrics such as the Fraunhofer distance, the direction-dependent Rayleigh distance, and the effective Rayleigh distance. The proposed band generalizes the previous conventional narrowband metrics. The second observation in this plot is that you can see that this contour plot has two asymptotes here. This leads us to our second result called as the aperture bandwidth trade-off. The question that we analyze in this slide is that what is the maximum available bandwidth available for a fixed beamforming gain, aperture, and incidence angle? To answer this question, we plot the maximum available bandwidth as a function of the beamforming gain threshold for two different angle of arrivals, 30 degrees and 60 degrees. Here we see that for a fixed center frequency, the maximum available bandwidth doubles as the aperture gets halved. We also observe that there is less bandwidth available when the angular coverage increases. The key takeaways from this presentation are: the bandwidth of a near-field distance determines the favorable region for a transceiver hardware operating at any general frequency offset from the center frequency. Hence, the important insight that we get is that a wideband system can leverage a larger bandwidth at the expense of a larger near-field region. The aperture bandwidth trade-off reveals that the array size or the bandwidth cannot be increased above a critical limit without readjusting the beamforming strategy to account for wideband and near-field effects. These fundamental trade-offs for phased arrays motivate new research directions for signal processing, antennas, and array design. Some examples are the research in tightly coupled dipole arrays, true time delay architectures, dynamic metasurface arrays, and codebook design and beam training for near-field scenarios. Thank you.